Already we have seen some problems on time domain analysis. Now let us see few more examples. Obtain the unit impulse response. Unit impulse response. What is the input? Unit impulse response means R of S equal to 1. And the unit step response means R of S equal to what? 1 upon S. This is the first input. This is second input. Obtain the unit impulse response and unit step response of a unity feedback system. Unity feedback system means H of S equal to 1. In fact, minus 1. H of S equal to 1. Whose open loop transfer functions, G of S is given. So we have to obtain the responses C of t for first case and the second case. G of S is given. We have to find H of S equal to 1. Therefore, T of S equal to G of S upon negative feedback. That's why 1 plus G of S, H of S, but H of S equal to 1. That's why we can write like this. That is equal to 2S plus 1. 2S plus 1 upon S square. 1 plus 2S plus 1 S square. So what you will get? 2S plus 1 upon S square. S square plus 2S plus 1 upon S square. S square getting cancelled. Therefore, 2S plus 1 upon S square plus 2S plus 1. If it is unity feedback system, the transfer function can be, T of S can be directly written like this. Whatever the numerator for open loop system is same as closed loop system. There won't be any change in numerator. That's why we can write numerator as such, 2S plus 1. No need to derive all these steps. Denominator equal to sum of numerator plus denominator. Sum of numerator plus denominator. What is numerator? 2S plus 1 plus denominator, what is S square? That's all. You got the same. This is only if unity feedback system. Numerator you have to keep as such. Denominator, sum of numerator plus denominator. That's why we can write like this. Numerator is same as numerator. Open loop. N of S. Open loop. Numerator plus denominator. So if it is unity feedback system, if closed loop, open loop transfer function is given, means you can find the closed loop transfer function simply by keeping the numerator as such. And the denominator is nothing but numerator plus denominator. Now we have to find the response for two cases. One is 2S plus 1 upon S square plus 2S plus 1. This can be factorized S plus 1, 2S plus 1 upon S plus 1 whole square. Can I factorize like that? S plus 1 whole square. S square plus 2S plus 1. So the roots are repeated. Roots are repeated. Roots are repeated roots. Minus 1 comma minus 1. Now T of S is what? T of S is output upon input R of S. That is equal to 2S plus 1 upon S plus 1 whole square. That is equal to R of S equal to 1. This implies for impulse, first case R of S equal to what? R of S equal to 1 impulse input, unit impulse input, unit impulse input. Therefore, what we will get is C of S equal to 2S plus 1 upon S plus 1 whole square. We know the response for underdamped system. In that case, what is the nature of roots? Complex roots. Zeta less than 1 means complex roots. Here, real roots, repeated roots. Already we know that the roots are complex. Roots are complex conjugate. Complex conjugate means zeta is less than 1. So, underdamped response. Underdamped response. For that, we know the derivation. That's why we can use the formula, we can write the response. Here we cannot, because the roots are repeated. Repeated means, what is the value of zeta? Repeated roots means zeta equal to 0. Sorry, zeta equal to 1. Zeta equal to 1. 0 means undamped. 0 means undamped. So, zeta equal to 1. Repeated roots means. In that case, what is the response? Smartest response. Smart response you will get. Smart response you will get. Third case, zeta greater than 1 means overdamped. Overdamped. In that case, roots will be again real and distinct. Real and distinct. In that zeta equal to 1 means roots are real and equal. Zeta less than 1 means complex. Here, the fourth case is zeta equal to 0, undamped. Undamped. It is oscillator. Undamped means oscillator. Always it oscillates with complex, with the constant amplitude. With the constant amplitude. This is the case. So here it comes in the second category. Real and equal. We do not know the expression for C of t. We have to find. That's why let us factorize this. That is equal to A upon S plus 1 plus B upon S plus 1 whole square. S plus 1 whole square. A equal to d by ds of S plus 1 whole square 2S plus 1 upon S plus 1 whole square S equal to minus 1. Therefore, these two getting cancelled. If we differentiate this, we will get to D equal to what? D equal to S plus 1 whole square 2S plus 1 upon S plus 1 whole square S equal to minus 1. These two getting cancelled. If we substitute S equal to minus 1, minus 2 plus 1 equal to minus 1. Therefore, C of S, A equal to 2, B equal to minus 1. Therefore, we are getting 2 upon S plus 1 minus 1 upon S plus 1 whole square. S plus 1 whole square. Now we can find C of t, Laplace inverse. C of t equal to, this is 2 constant e power minus t. A equal to 1 minus this instead of S square is there. Therefore, we have to multiply by t. S plus 1 whole square. Therefore, t e power minus t. This is the response. So, we have to derive no other way because we do not know the formula. Okay. This is for t greater than or equal to 0. Because the response is from t is greater than or equal to 0. What is the initial value? Initial value is 2. Initial value, if you substitute t equal to 0, you will get 2. C of 0 equal to 2. What is the final value? Final value. Final value you will get infinity, minus infinity, multiplied with 0, undefined, but anyhow, minus infinity. As a limiting case, you will get as a limiting case, you will get 0. Let us check final value theorem. What is final value theorem? It is not asked, but let us check. C of infinity equal to limit s tends to 0, s 2s plus 1 upon s square plus 2s plus 1. That is equal to what? That is equal to what? 2s square plus s upon s square plus 2s plus 1. Limit s tends to 0. Limit s tends to 0. So 0, you will get 0 upon 1, you will get 0. But here, if you check, if you substitute infinity, you are thinking that it is infinity, minus infinity. It is not so, because this is infinity, this is 0. 0 multiplied by infinity is undefined. That's why you have to find the limiting case. You can find this is undefined. That's why you have to find the limiting case. You have to find the limiting case. So while finding final value theorem will be very much useful. Okay. Now let us find the step response. Step response. For step response, R of s equal to what? 1 upon s. R of s equal to 1 upon s. Therefore, C of s equal to 2s plus 1 upon s multiplied by s square plus 2s plus 1. In other words, 2s plus 1 upon s multiplied by s plus 1 whole square. That is equal to a upon s plus b upon s plus 1 plus c upon s plus 1 whole square. If you factorize partial fraction. Now we have to find a. A equal to s 2s plus 1 upon s multiplied by s plus 1 whole square, s equal to 0. That is equal to 1. B equal to what? B equal to s plus 1 whole square, 2s plus 1 upon s multiplied by s plus 1 whole square. D by ds of. That is equal to provided s equal to minus 1. Therefore, that is equal to 2 plus 1 by s. D by ds of. That is equal to, if you differentiate this, what you will get? Minus 1 s power minus 1 s square, s equal to minus 1. S equal to minus 1. That is equal to minus 1. So B equal to minus 1. C equal to what? S plus 1 whole square, 2s plus 1 upon s multiplied by s plus 1 whole square, s equal to minus 1. That is equal to 2 plus 1 by s, s equal to minus 1 equal to 1. Therefore, C of s equal to 1 upon s, B equal to what? Minus 1. Minus 1 upon s plus 1 plus 1 upon s plus 1 whole square. That is equal to 1 If you take Laplace inverse, you will get C of t. C of t equal to 1 minus, this is what? E power minus t, at, a equal to 1. E power minus at, a equal to 1. Plus t, because instead of s plus 1, it is s plus 1 whole square. That's why t multiplied by e power minus at. That's all. In this case, what is the initial value? C of 0 equal to 1. C of 0 equal to 0. C of 0 equal to, as t tends to 0, this becomes 1. 1 minus 1 equal to 0. This becomes again 0. This also becomes 0. That's why C of 0 equal to 0. What is C of infinity? Final value. This is 1. This is also 1. This is, if you substitute infinity, what you will get? Infinity, e power minus infinity equal to 0. Therefore, undefined. That's why you have to find the limiting case. Limiting case. Again, let us apply final value theorem. What you will get is C of infinity. C of infinity. It is not asked. Let us find C of infinity equal to limit s tends to 0, 2s plus 1 multiplied by s multiplied by s plus 1, s square plus 2s plus 1. S equal to 0, you will get 1. S equal to 0, numerator you will get 1. Denominator s equal to 0, you will get 1. Therefore, 1. The final value is 1. But in time domain, it is difficult to find the final value. Difficult to find. You should be well versed with mathematics. Then only it's possible. Because it is undefined value. This is undefined. This is undefined. 0 multiplied by infinity is undefined. Why final value is required? Why final value is required? That we will see in the next class. Because steady state error is there. Steady state error means, suppose you are giving input, the reference is 1, but the system settles somewhere here. What is the reference? I want to ride the car at 60 kilometers per hour. But even if I give full accelerator, it goes only up to 58. It goes up to only 58. I gave full throttle, but it goes only up to 58. Then the steady state error is 2 kilometers per hour. Steady state error is 2 kilometers per hour. For that, we need the final value. What is the reference we know? R of s we know. In this case, R of s equal to what? R of s equal to 1. What is C of R of infinity equal to 1? Because step response means initial value and final value are equal. R of infinity equal to 1. C of infinity equal to what? 1. Just now we found. Therefore, error steady state equal to 0. Error steady state equal to 0. Reference also 1. Final value also 1. Therefore, error is 0. But in this case, it has some steady state error. Because the reference is 1, but it reaches only 0.98. Therefore, the error is 0.02. 0.02. This error is called steady state error. Steady state means after a long time. Steady state means after long time. We are giving input now. After long time, there is an error means that is called steady state error. So to find that, we need the final value.